Hi, this is Zhou Xiang from UIUC. Here I'm happy to present you our brief announcement paper, Be Prepared When Network Goes Bad, an Asynchronous View Change Protocol at PODC. This is joint work with Rati, Lefterius, and Alexander. As we know, state machine replication is a crucial part in permissioned blockchain, and if we look at the state-of-the-art SMR protocols, some of them are efficient under good network conditions, but if the network is bad, they lose liveness. While on the other hand, some of them are robust even under bad networks, but they are not that efficient when the network is good. And also, these SMR solutions are not adaptive to the actual network conditions. So the main question we want to ask and answer in this paper is if we can get the best of both worlds, meaning we want efficiency under good network, while we still have robustness and liveness under the bad network. So the short answer is yes. And in this table, we show a comparison of state-of-the-art SMR protocols and our new protocol. So Hotstuff is a partial synchronous protocol. It has linear cost under good network, meaning under synchrony. However, under asynchrony, it does not have liveness. VABA, on the other hand, is an asynchronous protocol that always make progress even under asynchrony. However, it always pays the quadratic cost even under synchrony. So our protocol achieves the best of both worlds, meaning our protocol can only have linear cost under synchrony and quadratic cost under asynchrony, and it's always making progress. So let's start by briefly introducing Hotstuff, or DIM-BFT, which is a production version of Hotstuff that also adds the view synchronization part. And as you can see from the figure, the Hotstuff in the steady state, meaning if the leaders are all honest and the network is synchronous, it can form a chain of blocks by the leader proposing its block and everyone voting for the block and send the vote to the next leader. And these blocks are linked by current certificate or QC, and each QC are formed by gathering enough votes from different parties. So as you can see, in the steady state, the cost of the protocol is linear because it's always leader sending messages to everyone and everyone sending votes to the next leader. However, if the leaders are bad or the network is asynchronous, the view synchronization part will be triggered and ensures everyone enters to the same view. In that case, the cost of the protocol will be quadratic, which is not showing here. So for the asynchronous protocols, we have VABA as the state-of-the-art. So VABA is a single-shot randomized BA protocol, and briefly it contains three parts: leader nomination, leader election, and view change. So leader nomination is basically each node running a Hotstuff instance, and after that they run a leader election to select one of the Hotstuff instance. If the selected Hotstuff instance does not commit a value, they will run a view change protocol and continue the next iteration. So as you can see, because there are many all-to-all communications going on, the cost of VABA is quadratic. So first, we'll turn the single-shot BA protocol into a SMR protocol. So we call this SMR protocol chained VABA. So similarly, the chain VABA will first running n parallel Hotstuff chains, then run a leader election that randomly picks one chain. All the nodes will then lock or commit according to the selected chain. Then the protocol can continue from the selected chain and again build n parallel Hotstuff chains and randomly select one chain and continue. Now let me briefly describe our intuition on how to combine Hotstuff and VABA to obtain our new protocol. So our new protocol has a steady state chain same as Hotstuff. So under synchrony, our protocol will be very similar to Hotstuff. Then if the network becomes asynchronous or the leader is bad, then all the nodes will trigger fallback and they will enter fallback. Each of them will act as the leader and propose and build its fallback chain. So similar to VABA, everyone will build fallback chains. Once enough fallback chains completes, the leader election will randomly select one chain out of these n-f chains. Then the steady state chain can continue from the selected fallback chain, and we go back to the sync path. Now let's briefly discuss the intuition of how our protocol guarantees safety, liveness, and efficiency. So for safety, our protocol always follows the safety rules of Hotstuff, meaning during the steady state or the fallback, the nodes will always follow the locking and commit rules of Hotstuff, and whenever they switch from the steady state to the fallback or from the fallback to the steady state, they also lock and commit according to the safety rules of Hotstuff. So you can view the steady state and the fallback chain as one chain, and basically it's one Hotstuff chain. So for liveness, our protocol guarantees one of the passes, meaning either the synchronous path or the asynchronous path will make progress. So there won't be a situation that both passes get stuck. So for efficiency, our synchronous path is the same as Hotstuff, so it's linear, and our asynchronous path is very similar to VABA, and its cost is quadratic. So to conclude, our protocol achieves the best of both worlds, meaning it has linear cost under synchrony and quadratic cost under asynchrony, and it always makes progress and is adaptive to the network conditions. So in our latest paper, we derive a two-chain version of our protocol, and we also have an implementation and many evaluations on the actual performance of the protocol. So if you are interested, you can check out this archive paper. So this is the end of my presentation. Thanks for your attention.